So our next video is regarding the dissociation curve, which is also called sigmotic curve or S-shaped curve. S, the letter in English, S. Like this curve is look like S-shaped curve, or sometimes called dissociation curve as well, and also known as the sigmotic curve in mathematics. So, what does this graph tell us? Initially, I told you about the partial pressure of oxygen, that the partial pressure of oxygen when increases, the percent saturation of hemoglobin also increases. This is what we look in this curve. Partial pressure of oxygen in kilopascal. When you are moving horizontally, increasing the partial pressure of oxygen, the saturation is going to be increased, because on the y-axis we say it's percent saturation of hemoglobin. So it means if we are on the peak here and we say it's higher saturation, it means there should be least saturation, and they are inverse proportion. If you talk about the dissociation, so here it will be the more dissociation because there's less saturation, and these two are opposing. Here in the previous video I told you that these two are opposite from one another. Saturation and dissociation are moving opposite. So if saturation is higher, then dissociation should be lower. In this graph which I have constructed right now, in this graph we are talking about the peak shows the saturation actually. So it means at this point higher saturation should be here, lower. I mean dissociation should be lower, but saturation is higher. Now the maximum partial pressure which I have seen here in this graph is 14, but although if you see at 12 kilopascal we got the maximum saturation of hemoglobin. This is because in the lungs the maximum partial pressure of oxygen, I told you in the chapter gases exchange, that is 11.2 kilopascal. So we cannot accommodate more partial pressure of oxygen in our lungs. So it doesn't make any sense if you write here 14, 16, 18 and 20 kilopascal, because in the air partial pressure of oxygen is 20%. But we can't take in account 20% here because there's no 20% oxygen in our lungs, because hemoglobin pick oxygen from the lungs, from the residual air. So we just consider that partial pressure of oxygen which is present in the lungs, and of course that is maximum is still 11.2 kilopascal. Again we are moving toward the 12 kilopascal here. So what this graph shows us, the most important thing, if you see the past papers, this question has been repeated so many times for 4 marks. And the question, why the dissociation curves look like S-shaped? If you see kilopascal partial pressure of oxygen 2. So at 2 kilopascal, the percent saturation is about something 10 or 11. Maybe it's like an imaginary graph. I cannot, I didn't construct it like with the scale, so maybe some discrepancies here, but if you draw it on the graph paper, that will be more accurate. So it's about the 10 something. But when we raise the partial pressure from 2 to 4, I mean we have doubled the partial pressure of oxygen. So if it is 10, it should be 20. But it's not the case. It's not 20, but it is 40 kilopascal. 40%, sorry, it's 40% saturation. Why not 20? Why 40? Because the same interval, if 2 kilopascal 10, so at 4 it should be 20, but here it's 40, not 20 actually. And in further increase from 4 to 6, bring a lot of change again, it's near about 78%. Why? It doesn't make sense. Why? If there's equal proportion, why not equal percent saturation? That's why we got a somewhat anomalous curve like S-shaped curve and dissociation curve. What is the explanation behind this? Now please focus what I'm saying. Hemoglobin has 4 prostatic groups, I told you. And the affinity of hemoglobin for oxygen is somewhat unique, different. I'm just giving you one example. Like for the basic knowledge, I'm just giving you one example. You have a container And in this container, you have 50 molecules of hemoglobin. So 50 molecule of hemoglobin means 200 prostatic group. Prostatic groups, isn't it? Because one hemoglobin consists of 4 prostatic group. I mean, 50 hemoglobin has the ability to pick up how many oxygen molecule? 200. And suppose we have here 200 molecules of oxygen as well. So what does our sense think? We say like, if there are 200 molecules of oxygen and hemoglobin also have the ability to pick up 200 molecules, so it should be immediately picked up, all these molecules, by the hemoglobin, isn't it? But that is not the case. It will depend on the partial pressure of oxygen, not on the number of molecules. Suppose these 200 molecules make a partial pressure of just 2 kilopascal. I'm just giving you an example, not necessarily that they have the same values, just for imagine. 200 molecules of oxygen makes 2 kilopascal, which is quite less partial pressure of oxygen. At such less partial pressure of oxygen, hemoglobin molecule take a long time to make its saturation. But still, the hemoglobin 200 prostatic group does not have the ability to pick up all this oxygen, and surprisingly, only 50, out of these 200, only 50 prostatic group will bind oxygen to make HbO2. It means I'm saying 50 molecules will be picked up and 150 molecule will be remaining in the solution. It means although we have a lot of oxygen still, but hemoglobin molecules don't like to pick up more oxygen. They become less saturated. Only one of the prostatic group per hemoglobin molecule. How many hemoglobin? 50. And how many prostatic group have been saturated? Only 50. Means one hemoglobin pick up only one oxygen, not all the 4-1. Now, what we are doing, that we transfer these 50 molecule, which is only one prostatic group has been occupied. Instead of HbO8, we have just only HbO2 because only one oxygen prostatic group have been occupied, 50 molecules. And we put this hemoglobin in another container. And here again, we have increased the partial pressure of oxygen, up to 4 kilopascal from 2. Or you can say, we just increase the number of oxygen molecule here, 200 more, to make 4 kilopascal. The same case here. You just can add, it's like equal to 2 kilopascal, the same molecule. If you are transferred to another container, then you have to add 2 kilopascal more pressure. And here, initially, 200 molecules more. So surprisingly, this time it will not pick up one oxygen, but each hemoglobin will pick up in the same time of interval 2 oxygen molecules. So it means among these 50 molecules, now we will get HbO6. Simply, we say, for simplicity, one is called Hb, which doesn't have any oxygen, and one is called HbO2, which picked up one oxygen. Now these are two different compounds. This is hemoglobin, and this is oxyhemoglobin. When the oxygen binds with the hemoglobin, it brings certain types of changes in the hemoglobin molecule, dissociation. And these changes enable the hemoglobin molecule to make it further more reactive to the rest of the oxygen atoms or molecules. Initially, it is very difficult for the hemoglobin to pick up oxygen. But once it picks up oxygen, then further addition of oxygen can bring a remarkable saturation. It means what I'm saying actually, hemoglobin molecule has lesser affinity for oxygen than for oxyhemoglobin, because this oxygen further make it hemoglobin more active. This is what the case which we have seen in the enzyme chapter. I told you induced fit theory. When the substrate molecule bind with the enzyme, it makes it more reactive, so it pick up rest of the substrate molecule more readily. The same case here. Now look at the case here. In this case, this saturation makes actually oxyhemoglobin. But when we add more partial pressure, so it brings a remarkable increase in the partial saturation. This interval is not the same. It means by increasing the partial pressure of oxygen, we can increase the affinity of hemoglobin for the oxygen molecule. And that's why it's curved like, this is why this curve is lesser, because lesser oxygen has been picked up at 2 kilopascal. But when the partial pressure is increased at the same interval, this time more oxygen atoms have been picked up. Why? Because now hemoglobin become more active as compared to the first status. That's meant by increasing partial pressure. And once you further increase, it also make hemoglobin more reactive until saturation takes place at 12. So the summary, hemoglobin molecule have a certain type unique feature. At low partial pressure, if there is lesser partial pressure of oxygen, percent saturation of hemoglobin takes place, but very slowly. Once only 25% saturation of hemoglobin takes place. Now this hemoglobin is quite changed from the initial hemoglobin, which do not have any oxygen. Now this hemoglobin, which have oxygen, 25% oxygen, and it means like oxyhemoglobin. Now it is more reactive than hemoglobin. So if you just provide little more partial pressure of oxygen, it will pick up oxygen with a more faster rate as compared to the initial rate. And that's why it's even a slight increase, only a slight increase in the partial pressure can bring a remarkable change in the percentage saturation of hemoglobin. That's we see, in this curve can be seen. Why this curve is sigmotic? Because why this curve is like S-shaped? Because at low partial pressure, lesser saturation of hemoglobin takes place. Slight increase in partial pressure makes the affinity of hemoglobin more with the oxygen, so more saturation. It remains continued and until finally it becomes. Now there might be a question in your mind, if it is steeper, if from 2 to 4 is steeper, but why after 6 it's become again less steeper? Yes, this is a question. This is because that all the active sites of hemoglobin now are going to be saturated. And you know that when the product is increasing and the substrate active sites remain decreasing, the rate again slow down. So this is because all the prosthetic group have been occupied, so the rate become constant now. That's the reason. If you further increase the partial pressure, it doesn't make sense. It cannot increase the saturation because it's fully saturated now. And that's the case we can see here in the dissociation curve. So what was the conclusion? At 2 kilopascal partial pressure of oxygen, least saturation of hemoglobin takes place. However, a slight increase in the partial pressure of oxygen from 2 to 4 brings about more saturation as usual, because it is now oxyhemoglobin which has more affinity for the next oxygen, for the next prosthetic site. Steepness remains continued until all the active sites have been occupied. So 6 to 8 partial pressure and about 10 and then 12 is the maximum partial pressure at which saturation become completed. And that's called the sigmotic or dissociation curve. If somebody asks you, what about this curve and what will be the effect of increasing the concentration of carbon dioxide on this dissociation curve? So look, I'm just going to compare these two sites. One's this one is here, 2. If somebody asks you, in these two sites, which one is the active muscle and which one is the resting muscle? Resting muscle, active muscle. Resting muscle means you're not working something and you are relaxed. So the rate of respiration is quite lower and it's not high metabolic rate. But active muscle means high metabolic rate. Tell me, where should be the dissociation high? In the resting muscles or in the resting muscle or in the active muscle? Of course, in the active muscle, because active muscle have a high rate of respiration. High rate of respiration means more carbon dioxide. More carbon dioxide means acidic environment, and high temperature, which means higher dissociation. Isn't it? So it means it should be the active muscle, active, and it should be the resting muscle. Isn't the case? Here should be higher dissociation because of carbon dioxide, high temperature and acidic environment. And here should be the resting muscle. And that's why in resting muscle we have high partial pressure of oxygen, because oxygen cannot be unloaded, here more oxygen is unloaded. So if I'm constructing one graph more, what will be the effect of carbon dioxide? What will be the effect of carbon dioxide partial pressure on the dissociation curve? Suppose throughout this curve, carbon dioxide partial pressure is constant. So here is the partial pressure of carbon dioxide, which remains constant throughout the process. So I'm just going to rub because it makes like confusion. So rub here, right? So carbon dioxide. These are the partial pressure of oxygen is changing, but the partial pressure of carbon dioxide throughout this curve remains constant, right? Now I'm just going to make another graph where the carbon dioxide concentration is higher. I'm just going to make another curve where the carbon dioxide concentration is higher, means higher partial pressure of carbon dioxide. So what do you think? The curve should be shifted toward the right or toward the left if I'm increasing the carbon dioxide concentration. If the carbon dioxide concentration is higher, then dissociation should be higher. If dissociation should be higher, saturation should be lesser. Saturation should be lesser, so the curve should be shifted toward the right. The rate become slows down. So another curve, same format, like it will move this way, like here. Not this one, like this one. So here we can see partial pressure. I'm just going to the blue marker. Here is the partial pressure from black, and here through the red partial pressure of carbon dioxide. So where the partial pressure of carbon dioxide should be higher and where should be lesser? Which rate is faster, steeper? Of course, the black one. The black one is steeper, so it means saturation is high because this is saturation. And the red one has lower saturation. So it means indirectly, red one has a higher dissociation. So it means this carbon dioxide is higher than the partial pressure. So it means partial pressure of the red one carbon dioxide is higher than the partial pressure of carbon dioxide in the black one. So when we increases the partial pressure of carbon dioxide, we are shifting the curve toward the right, isn't it? The right. So the partial pressure for both the curves remain in the same format, changing with the same intervals, but the partial pressure of carbon dioxide for both the curves are different. This curve throughout high partial pressure of carbon dioxide, and this curve throughout low partial pressure of carbon dioxide. So now we can simply say that if somebody asks you in this graph, I'm just giving you 4 locations, like one location is here, this is A, one location is here, this is B, one location is here, this is C, and one location is here, that is D. And this is my MCQs from questions. If somebody asks you A, B, C, D, which one is the active muscle? Which one is the active muscle? So think about that. Active muscle means high dissociation, isn't it? High dissociation. because we are in the demand of oxygen, in the active muscle, in the demand of oxygen. So if you have a demand of oxygen, there should be more availability of oxygen. And oxygen can only be available if there's a higher dissociation, unload of oxygen from the hemoglobin. So if you are in the demand of oxygen, mean higher dissociation. So first of all, compare these two curves. Forget about these points. Two curves. Which curve has a higher dissociation, the red or the black? Higher dissociation. Of course the red. Higher dissociation, the red. Higher saturation, the black. But we are talking about the higher dissociation, which should be the red. So ignore these 2 points. We are not coming to these 2 points. Because our answer should be in A or C, as we are talking about the higher dissociation. So both A and C has a higher dissociation than B and D. So forget about B and D, and let's talk about the A and C. So curve-wise, if you compare the curve, we selected the red one for dissociation. Now the point-wise, calculate which one has the higher dissociation, A or C. Of course the C, because it has least saturation as compared to A in the same curve. So our answer is C. C is the active muscle. And A should be some other tissue, resting muscle maybe, and maybe B in the lungs, and D some other muscles. So that's the question. Sometime if you look the past papers, there's a lot of questions regarding the shifting of the curve and then the partial pressure of oxygen. So this is all about the partial pressure of oxygen and dissociation curve, and we will see you in the next video regarding the Bohr shift and some calculations about the chemical reactions. We will discuss the mechanism, the chemical mechanism of all this process in the Bohr shift, and then we will move to the next topic, with the cardiac cycle, inshallah, and we will close the chapter then after a few topics. See you. Thank you.